All right, so my name is SarahMaurer, and I am a associate professor at Central Connecticut State University. I titled my talk based on the title of the session, but I, as you can see from this background image, primarily work with prebiotic membranes. So I try to form primitive cells. And my work has been very heavily influenced by my funding through both NSF and NASA. My NSF funding is actually a collaborative project with Lauren Williams at Georgia Tech, Mike Travisano at UNM, and Paul Bratcher at SLU and St. Louis University. And part of the ideas that have taken shape over the last few years in my personal research was shaped by a sabbatical that I did in the Williams lab in 2020. And so just before the pandemic hit, I had a sabbatical at Georgia Tech. I have a lot of student researchers that have contributed to the work you'll see today. They're listed here. Actually, there were more student researchers that have contributed, but these are the most recent set of students. And so I thought they were appropriate to include. And one of the foundational concepts that I use in working with prebiotic chemistry is that I really try to use mixtures that are prebiotically relevant. So either found in like extraterrestrial delivery sources or through geochemical reactions. And we try to use those to understand both how early cells could form and what their function would be. So I'm going to talk about both the formation and function of protocells today, hopefully not stepping too much on Dave Deemer's toes. Let me just close my door. Sorry about that. It's weird having people in the office. Okay, so some of the formation conditions that are really important for primitive membranes to form is, one of them is pH, and this has been known for a really long time. There's a lot of literature on this. So for fatty acids, for example, Dave originally published, and we've known since the 70s that at low pH, fatty acids are in the COOH form, and they tend to be pretty oily. In fact, if you drop the temperature, they actually crystallize into solids. If you raise the pH so that half of your fatty acid is in the acid form and half is in the carboxylate, the deprotonated form, that balance of charge and polar head group is going to allow vesicles to form. And if you deprotonate all of your fatty acid into the carboxylate form, then you get very small micelles. And for the origins of life, we really like vesicles for a number of reasons. One is that they have an aqueous interior. Two, they look a lot like cells, and there's something about, things that look like cells that make us consider the origins of life. But then also, micelles are really, really dynamic, and so they exchange with the aqueous solution very, very quickly. The deprotonated form, the carboxylate form of these acids actually is pretty soluble in water, depending on how long the hydrophobic chain is. And so you get a lot of exchange with the solution in micelles, and they turn over pretty quickly. And oil, while it's convenient because it will solubilize hydrophobic molecules, there's no way to really get hydrophilic molecules to stick around in them. They associate electrostatically with the surface. So vesicles are like a convenient mechanism for forming early cells because you just pH adjust some georeactant extract and you get like these nice vesicles in solution, ideally. But it turns out that if you have mixtures, so if you're not working just with fatty acids, so here, looking at some work by Trishul Namani and Dave Deemer, while I was a graduate student in Dave's lab, the vesicles can form at high pH. So on the x-axis or on the y-axis, we have pH, and you can see that at high pHs, we get vesicles to form with a mixture of decanoic acid and decylamine. This is because at high pH, our decanoic acid is deprotonated, so it's in the negative form, and the decylamine is neutral. It's the NH2 form, not the NH3 plus. And so a charge with a neutral molecule at high pH forms these membranes. When you have two charged molecules, so the decylamine protonates and becomes positively charged at about pH 9, and then you start to see crystalline solid because the decanoic acid associates really strongly with the positively charged amine, and there's a bunch of crystals in solution. And then once the decanoic acid protonates and becomes a polar molecule, more oily with our positively charged decylamine, we start seeing vesicles again. So depending on your mixture, you can have a solution that has vesicles at more neutral pH or that has vesicles at extremes. And one of the things that we asked in my lab was, well, you know, what do these mixtures look like? What's the probability of seeing different mixtures? And one of the things that we know is that addition of fatty alcohol or glycerol monodecanoate to decanoic acid at high pH actually stabilizes the decanoic acid vesicles. So we have a number of ways of mixing these small amphiphiles to get vesicles at high pH. It turns out that other mixtures are capable of forming vesicles at low pH. So my lab looked at not just decanoic acid, which has this deprotonated form at around pH 7. But we also looked at decyl sulfate, we looked at decylamine, we looked at decanol, and we looked at glycerol monodecanoate. And we mixed them in binary mixtures just to make things a little more simple. And what we saw is that we actually get vesicles to form under a wide range of conditions with a lot of different mixtures. So you can see that negatively charged amphiphiles with a neutral decanoic acid. So this first column is pH 2, or the second column is pH 7. I didn't include any pH 10 images because, as we know, this glycerol monodecanoate decanol decanoic acid works really well at high pH and has been published quite frequently. One of the interesting things is that even though the protonation state doesn't always change, the morphology changes as we change pH. So if you look at our decanol decylamine mixture at pH 2, we have a lot of very multilamellar vesicles. They tend to be stuck together. As you increase the pH to pH 7, so this is the same mixture just at pH 7, we see a pretty decent change in morphology. And so while we are still forming structures, we assume that there is some transition that's occurring between these two sets of molecules, or between these two morphologies. And thank you. And there's a pretty consistent feature where if you have a charged molecule, so at pH 2 and pH 7, decylamine is positively charged, with a neutral molecule, that we are likely to see membranes. So here we have a negative charge with a neutral molecule, a positive charge with a neutral molecule, or an uncharged molecule, right? And here, negative charge with an uncharged decanoic acid at pH 2. So essentially, there seem to be rules for how these mixtures form. If you have too much uncharged molecule, it tends to be very oily. If you have too much charged molecule, it tends to be very soluble. So for example, decyl sulfate forms micelles, right? It's the like dodecyl sulfate is a soap additive. So the highly charged molecules tend to be micellar. And so a good mixture would have some balance of charged and uncharged amphiphiles. And I think this is a really cool result, right? There are lots of different mixtures that could form membranes. And so if we just have hydrophobic aggregates that are floating to the surface of lakes or oceans or tide pools, these hydrophobic aggregates are very likely to form and self-assemble into things that not only are, you know, kind of oily, so these very dark spots are pretty hydrophobic, but things that look like membranes that have an aqueous, very clearly have an aqueous interior, those are likely to have formed from just basic, simple organic molecules. All right. The other things that we have considered for formation conditions are ionic strength. So it turns out that if you add too much salt to a biotic system, that it tends to precipitate out, and this is true for proteins or DNA. And you can see the same thing with amphiphils. It also turns out that you need a small amount of ionic strength to get vesicles to form. Specifically with fatty acids. So for years, people thought you had to like take vesicles or take decanoic acid to a high pH before it would form membranes. And it turns out that you don't. You just have to add enough salt that the decanoic acid becomes less soluble in water, right? The water activity changes as you add sodium chloride, and it actually forces the decanoic acid to form these hydrophobic phases at even small concentrations of sodium chloride. Note that for things like oleic acid, they form much more easily. And so if you have hydrophobic enough materials, they don't actually require salt. And specifically like phospholipids that form our modern cell membranes definitely don't really require salt to form vesicles. But the other thing that has also been known for a very long time is that, and this is part of Dave Deemer's work, and Pierre-Alain Monard has done a lot of this work in addition to myself, where if you add a second surfactant, so something like glycerol monodecanoate, that you can actually get stability under both divalent cation conditions or high concentrations of monovalent cations. And so mixtures, again, for the win, right? Having a mixed vesicle system makes our vesicles or makes our membranes, our protocells, more robust. And so are there any other conditions that matter? Is there anything else that we should be considering when we're talking about protocells that I haven't really discussed here? One of the things that I have been thinking about pretty heavily is that we don't really use, when I say prebiotic realism, we don't actually ever include minerals in our reactions. It's just difficult to have minerals around that would have been around on an anaerobic early Earth. And so it's very unknown how protocells are going to really interact in the presence of a diverse mineral environment. There has been a little bit of research on this by Nita Sahai, who I know was here yesterday, and she has shown that amphiphils will charge associate with mineral surfaces, and that they actually form multi-layered bilayers that kind of coat the surface, which if you're someone who does like AFM, you know that these surfaces get coated pretty easily, and it's no surprise that these surfactants do that too. The other condition that we haven't really talked about, but Christian Mayer talked about yesterday a little bit, is that we don't really know a lot about pressure and how it impacts the fluidity of single chain amphiphil membranes. So we do know that it can impact the phase transition of like phospholipid membranes, but it's not clear how these prebiotic amphiphils are impacted by pressure. And so that would be a cool condition to kind of think of for future use. Okay, I want to move on to the second part of my talk, which is talking about how functionality can occur in these membranes. And I just kind of picked a few functions that we have been looking at in my lab. So this is work that was done by a master's student in our biomolecular science department. And she was looking at the formation of these cyclobutene pyrimidine dimers in DNA. So sure, this is not very prebiotic, but there was a very convenient ELISA assay that could measure the amount of CPD DNA that was formed in a DNA sample that had been exposed to UV light. We were specifically using genomic DNA, like the salmon testes DNA, that had been sonicated to small pieces. And we encapsulated it either in phospholipid vesicles in the same phospholipid vesicles, but containing about 100 micromolar of a polycyclic aromatic hydrocarbon. We used pyrene, which is one of the most abundant PAHs that's detected in the Murchison meteorite. And then we also looked at a no vesicle DNA sample. And what we saw is that over our 5-hour time period, the amount of mutated DNA was very high in our no vesicle sample, and that there was very little CPD formation in either one of our vesicle samples. I know it looks like vesicles with PAHs is lower, but I think it was not statistically significant in this case, whereas in the 1.5 and the 5-hour no vesicles compared to vesicles, there was a significant decrease in the amount of formation of CPD. And so vesicles can protect encapsulated material, including genomic material, from things like UV light. UV light is one example, but I know that some people have looked at, for example, hydroxyl radical forming compounds that are put outside of vesicles. So it could protect it from things that are outside the membranes as well. In addition to protection, membranes can be part of what we think of as our first primitive life cycles. It's actually pretty easy to get vesicles to grow and divide because they are hydrophobic. So if you put more hydrophobic material into solution, either something that is very oily or something that is amphiphilic, the amphiphile or the oily molecule is going to spontaneously insert into the membranes, and those membranes are going to grow from a very small size to a very, very large size. And so this is work for my PhD thesis. But that once you get a vesicle to grow, you can also get it to divide. And the Shostak lab has found a few different ways to get things to divide. So you put in energy essentially, and you can get these vesicles to divide. The last function that I want to talk about is the focus of my current NASA grant, which is to try to get a chemical gradient to form within our membranes. How we do this is we take light and we excite a polycyclic aromatic hydrocarbon that is membrane bound. Here, this is fluoranthene. It will donate electrons to a carbon. Here, we're using carbon dioxide or bicarbonate. And we produce formate. We actually know we produce formic acid, well, formate, the 45 mass formate, because we can detect it in our GC mass spec. And we can use a diversity of electron sources to regenerate our polycyclic aromatic hydrocarbon. It's actually been known for a long time that something like this kind of happens. I say long. So for example, Dave Deemer, who's talking today, showed that when you take a system much like this, I think this was done in oil droplets. Oh no, it wasn't. It was done in vesicles, that you can get a very rapid formation of a pH gradient inside the vesicle, and that you can release that pH gradient by adding some ionophores. And so we've known for a long time that there's something that is generating a pH gradient inside of our membranes, but this more recent work shows that we're actually detecting formic acid as one of the products. There are likely a few other products as well. We see degradation of our decanoic acid, for example. And that we can get this to occur in our prebiotic membranes as well as in modern phospholipid membranes. And so having a chemical gradient form is very important to the start of energetics. Also, I think that this was something that Bill Martin was talking about yesterday, where having a sustained synthetic reaction is really important for generating life. You can't just hope that like decanoic acid shows up in solution so that you can make more membranes, although maybe you can for membranes because they're so robust. but for metabolism that you really need something that's going to be synthesized through the course of the reaction. All right, and so essentially what I've been talking about is how we can use vesicles for chemical evolution, some of the functionalities that we can see. And I think the other talks that we're going to see today tie into the idea of chemical evolution from different standpoints. So when we think about chemical evolution, we usually think about chemicals that independently form something like a precursor to information, a precursor to metabolism, maybe a precursor to an enzyme. And some of these are interlinked, right? Like a precursor to the ribosome. And then at some point, these independent entities start being in some way dependent on one another. And so maybe they're dependent on functional membranes, but maybe the functional polymers, like two copolymers, are coexisting. And eventually we get to this integrated genetic metabolic contained system that we can call first life, right? This is like the big dream of me and many of my collaborators. And so hopefully today you will hear a good deal about how this chemical evolution occurs. So Moran Frankel-Pinter is going to talk a little bit about protopeptide formation. So this is kind of the idea of how do we form early enzymes, or how do we form even, I mean, thinking about peptides as an information polymer in some sense is not out of the question. And so these are early kind of metabolic or enzymatic materials that form, and specifically how we can form those through these thiol groups. And so we have someone that's talking about kind of the metabolic enzymatic process, but additionally, Sieber and Otto is going to talk a little bit about how networks can form in our kind of chemical evolution and what those molecular networks need to do to be lifelike. And so how can you get lifelike features out of molecular networks? And you can imagine how this ties really well into how we generate protopeptides and also formate from carbon dioxide. And then Dave Deemer is going to tell us a little bit about the path to protocells. So I told you about the formation of simple amphiphile vesicles, but hopefully Dave is going to elaborate a little bit more about how we can form the first cells from these structures. And then finally, we're going to hear from Christine Keating, who is going to talk a little bit about coacervates. And coacervates are really cool because they can help, as you see down here, they can help RNA to actually function. And so I'm sure that she will tell us a little bit about how coacervates can act kind of as like a protocell for our RNA, or our first information systems slash early catalysts, right? Because RNA is catalytic. All right. And so I just wanted to kind of finish up by talking a little bit about the future directions that people who are trying to understand chemical evolution, including myself, are really interested in. And I think that we approach this from not just a protocell perspective, which is what you've heard a lot about in my talk, but also from a metabolic perspective. And so thinking about how we can tame messy chemistry, meaning if there were a lot of organics around at the origins of life, how did we select the 20 amino acids that we're currently using? I'm sure you'll hear about that today. Also, how do we get to phosphorylation or other forms of chemical energy like sulfur compounds? We also have a lot of questions about information and thinking about using polymerization as a selection mechanism, which I'm sure Dave will talk about, and how coacervates and membranes interact. And then finally, what you will not really be hearing about today, but is something that we should all be considering, is how mineral surfaces are actually impacting these assemblies, and also how those minerals are coupling to our early metabolic processes that we're trying to achieve within these protocells. And so I think that this is my last slide. And so I'd love to take any questions that you have if we have time. I know I was late, I'm sorry.
Thank you very much, Sarah, for the